of what we discussed in class. It won't be the whole 90 minutes because obviously y'all work within your small groups of time. I'm not going to film that part, but I do want y'all to have that resource. When we get to using Carnegie Learning, that's what's in those boxes back there. That's our new curriculum. There's actually videos that professional videos that Carnegie Learning has already created for every single lesson that we use from the Carnegie Learning curriculum. There's also an adaptive framework there where you can actually practice questions that go along with the unit, and as you get them right, it helps you progress through the unit and master the material better. So I'm really excited about that curriculum. Alright, so here's an example of what I'm looking at when I say justification. I don't think y'all can read that very well. Let me make this a little bit bigger. Should have thought about that before. So this is a student I had last year, and I'll move it up so you can see the bottom. But I want you to notice how this student is scoring 5s and 6s up here, right? Because what we're doing is we're simplifying expressions here. By the way, why do we know it's an expression and not an equation? Why do we know these are expressions? Okay, it's got parentheses. You don't have to have parentheses to be an expression, though. It's not equal to anything, so it's not an equation, right? Remember, we defined expression yesterday. You need to know the definition of an expression. It's a combination of variables and or numbers through mathematical operations, right? That's a combination. And it's not a statement of anything. It's not equal to anything. It's not greater than anything. It's just there, right? It's an expression. It can represent things. But notice right here with this work, right? He showed me this work, but also he made a quick note of distribute the binomial. That's why he got a 6. Because he didn't just show me algebraic work, he made a quick note. It doesn't have to be long, but he said distribute the binomials. When he says that, do I know that he understands what to do with this expression? Yeah. Yes, very much so. And so it's not just about punishing you or not giving you full credit for something. I need to know how well you understand things. If you look at some of your pre-assessments, you'll realize, like, yeah, I have work here, I might have the right answer, but can you guess the right answer on multiple choice? Yes. Does that tell me how much you really know? No. I want to know how much you know. I need to know that, and that way I can give you feedback. Notice, which all of this is his notes, that's not any feedback. But right here, so 5.5, very high score. In fact, remember, 5.5 average, that's 100, right? So he did all this work. He got the right answer, right? 5.5 tells me he got the right answer. And so he made some notes here of substitute 4 for x and proceed to using order of operations. Phenomenal, right? But he said solve right here. Notice I marked through the word solve and I said simplify. Because I'm giving him feedback to improve his understanding, right? Solve implies finding a value that makes the equation true. That's not what he's doing. He's taking an expression, he's simplifying it. When you show me and explain things like this, I can give you feedback so that you can improve your understanding, okay? That's what it's all about. It's growth, right? And so I want you to notice those kinds of things. And if you look at this lower stuff here, and this is where I'll stop, right? So we get a 6, right? He explains that it's quadratic because he distributes and shows that the highest power is second, so it's a quadratic function. Down here, he tells me it's a quadratic because, nope, that's not what I wanted. There's something else. I don't remember what I grabbed this for. Sorry for lying to you people. There's another reason why I grabbed it, but I don't remember. But that's how I give feedback overall. And I just don't see it anymore. But notice it's not just showing work, it's explaining just a little bit. Even if it's 3-4 words, it's showing me what you know about that topic. Does that give us a little bit better insight into what I'm looking for when it comes to justification? Yes, yes. By the way, I do want to point this out. This was the very end of the year, okay? This is a student who had me for probably 3/4 of a year, a little over 3/4 of a year. I'm not necessarily expecting you to be perfect at justification right away. I expect us to work towards this. But I'm going to constantly show you examples of what I'm looking for so that you can improve, right? I'll show you some of your own work without the names there so that we can critique it and improve our understandings, right? So please be aware of that. I want y'all to be able to grow well. Okay, so getting back to yesterday, all right, when we got to lesson 7, we wanted to explain why some algebraic moves create equivalent equations, but some do not. We want to know how equivalent equations are related to the steps of solving equations, and we need to know what it means for an equation to have no solutions and can recognize such an equation. So we did this yesterday about 0 being the solution. We got to this point and there was a little bit of confusion, so let me clarify a couple things. Okay? If you read these directions, choose a pair of equations from column A. Explain why, if x is a number that makes the first equation true, then it also makes the second equation true. When is the only time that a pair of equations will always have the same solution? I mean, yes, it's a solution, so it'll make both equations true. But when will a pair of equations, they look different, but when will they still have the same solution every time? You're close. There is an E word that we want to think about. Say it again. If those equations are equivalent, right? The whole point of equivalency is that they make both, or that those equations look different, but they're still effectively the same, right? So, what can we use to show that equations are equivalent? Come on, I want y'all to be able to work so you can talk and have more fun than just listening to me, but we got to get this part out of the way. So show how equations are equivalent. What do we need to use to show that equations are equivalent? Say again? I mean, you can work them all the way out and solve for x. You can totally do that, but there's an easier way. There was something we talked about yesterday. Properties of equality, right? If you can use a property of equality and get the same equation, then those equations, the original ones, must be equivalent. Okay? Say again? Okay, that's a good question. So let's do number 2 together. Let's look at this one. Does anyone see a way that I can use a property of equality to quickly get the same equation without having to solve it all the way? Yes, ma'am, Jada. Can I subtract 2x? Notice it's adding 2x, so I might subtract it. And from the 5x? Say it a little bit louder. Okay, so if I subtract 2x from 5x, I'm going to get 3x, right? Right? And so, okay, so let me ask, yes, that's correct. Yeah, just make sure that we use a property of equality and we do it on both sides of the equation to keep it equivalent, right? So we subtract 2x here and we have to subtract 2x over here, right? And so that does give me a 3x and that gives me a 0. Now we have literally 3x equals 24. So are those the same equation? Yes. Did I have to finish working all the way out? The point is that the properties of equality make those equations equivalent, right? So we know they'll have the same solution.
Number 1 is just multiplication.
Is a multiplication property of equality? What multiplication, what are you doing? Which multiplication are you doing?
I did 4 times 9 and 4 times the x. I got the same one.
So a property of equality is telling us whatever I do to one side of the equation, I got to do to the other to make it, say, equivalent. Am I doing that here? I'm using multiplication, yes, but there's another property. Say it louder, yeah. Distributive, right? So notice there's a difference between distributive and that multiplication property of equality. You with that? Okay. One other thing I do want to point out is it doesn't have to be the subtraction by 2x. Can I add 2x to both sides? Is that going to maintain equivalency? I mean, yeah, it maintains the equivalency. In terms of solving it, would it make sense? But what is 3x plus 2x? Is that the same equation that you started with? So, is there more than one way to show that two equations are equivalent? Yes. And I just want you to see that, okay? So what I want you to do, you don't have to do all of them. Let's pick 3 sets of equations from column A, 3 sets of equations from column B. Remember, column A, we're trying to show that the equations are equivalent. That's why they have the same solution. Notice for column B, it says why the second equation is no longer true for a value of x that makes the first equation true, which means those equations are what? If they don't have the same solution, they are not equivalent, right? So that's what you're trying to show, okay? Please work on that. You just have to do 3 sets from A and 3 sets from B. Let's get to work. Let's try to finish it up 15 minutes or so. At least within 15 minutes. I don't think it should take that long. Okay, so Gracie's not here.